So the intro is, my credentials are, I was working on Java for a long time, back at Intel, at Sun, and now at Oracle. I'm responsible or guilty for numerous projects like Aurora, Spec JVB, and all sorts of concurrency improvements, and Java microbenchmark harness, for which I will talk today, and Java concurrency stress tests, which I should had the lightning talk like 15 minutes ago, right? Okay. So let's start with the basics. I expect this audience will have the answer to this question. What's the benchmark? Nobody knows what the benchmark is? Okay. I actually argue that the things that we call micro benchmark, these micro workloads that we are measuring, we need to get the units straight first. The word micro suggests it measures the effects measuring in the microseconds, right? So it's like the single web app request or some very very tight operation or something like this. But most of the people, when they do benchmarking, they actually do something like nano benchmarks, when they measure the effects of counting in nanoseconds, like single operations. So if we do this upwards, we will see that there are milli and just benchmark and kilo benchmarks and maybe mega benchmarks like SpecJ Enterprise, which takes like 3 performance engineers to set up and run. And the idea is, for this distinction is you have all these different pitfalls in all of that levels, right? You can also see the pico benchmarks, which you measure the effects on sub-CPU clock level, like the pipelining and all that stuff around. These are very hard to do. One of the slides that we like to talk about in our Russian demos, when we say the performance engineering is somewhat strange, because we start to deal with our systems by the means of natural science. While we humans are responsible for technology on each and every level, we build CPUs, operation system, and whatnot, it's easier for us to get this black box mindset and build the high-level models of how this all complex interactions between hardware, software, and data is there, and build the high-level models by which we can infer the reasoning about how all systems perform under load, under different conditions, and whatnot. When we do this natural science, we have to do experiments. Our ultimate tools for conducting experiments in performance areas are benchmarks. And every single benchmark requires control. So that means that if you do the benchmarking, you have to have a set of baseline experiments. Sometimes you are fine with just a few. In many cases, you have to have a web of experiments that are trying to prove that all others are correct. As the software guys, we actually have the very nice feature we can peek under the hood, right? Like we can look at the disassembly. Physicists will probably kill us for that feature in their area, right? So you can disassemble the universe and see how the quarks are actually interacting with each other. They don't have that opportunity. We have, right? So the benchmarking assumes the performance model in this sense, right? We are not just measuring for numbers. We are trying to prove that our performance model that we have for the particular system is correct or not correct, and what should we do to fix that, right? So the common wisdom is micro benchmarks are bad, right? Who heard about this? Cliff, are you there? OK. I'd say that this is not true. Micro benchmarks are not really bad, right? I think when the people talk about micro benchmark, they say, well, micro benchmarking leads to the premature optimizations, right? And that's the all evil, right? So not the benchmarks per se are evil, but the premature optimization decisions that we do basing on the decisions from that micro benchmarking is what's evil. And I'm a very humble person, so I like to elaborate on the famous people quotes. So I have another quote from me. I actually argue that the optimization is evil, not really the premature optimization, right? Why is that? Well, because optimizations break our assumptions about flat performance model. They distort the performance model that we have, right? We are usually say that we do the optimizations that are applied in some common cases, but it really makes that common cases special, right? There are unclear interdependencies between optimizations. And while there's the black box abstraction for the functional wise, right? We can compose the software from the modules and infer the functionality from it. For performance, it just breaks badly. You can't measure the module A and then module B and then try to compose the performance metrics from these guys and say how it will perform together, right? As the example for this thing, suppose you have the implementation for the language X, interpreter and compiler. Which is easier to benchmark? Who's for interpreter? Who's for compiler?
Do you have third choice?
Hmm?
Do you have third choice?
Like what?
Incorrect question.
Yes, it might be incorrect question, yeah. So this is more correct question. Suppose I am Java and I have this new object written somewhere. Oops, what's that? Woo. OK, that was just the screensaver. Don't worry about it. So the performance of this thing really depends on multitude of questions, right? Whether that object was allocated in thread local buffer. Was it large enough so we had to promote it prematurely to the large object area? Was it scalarized so JIT actually eliminate the allocation of this object and use the field instead? Or we don't even use the field, so there is no object at all, right? So this kind of distorts our perception of that my object having the single performance cost in all the cases, right? So the rule from that is, so the benchmarking, while we do benchmarking to do the optimizations, the benchmarking per se is the fight against the optimizations. Because we have to level out the performance model before we can try to infer something from the benchmarks, right? So we can get predictable results. Or we can isolate the optimizations that we don't want to and instead contrast the optimizations that we are after. So the end game for benchmarking is not numbers. It's just not. You can't just say this is faster by 10 times. The end game for benchmarking is understanding the performance model of your system to actually gain the intuition about what will happen when system would transit to the particular state, or it will be presented with a different data or whatnot, right? And so while if our end game result is understanding the performance model, that means that every single optimization, every single smart trick and smart hack that we have in our runtime operation system hardware is the potential hassle for the benchmarking because it can distort our assumptions, right? So we wouldn't be a serious company if we wouldn't have our own benchmarking harness, right? So we have GMH, which is there in OpenGDK. It works around many of the hotspot-specific and OpenGDK-specific pitfalls. We also learn a lot about VM as we go. And so we fix a lot of stuff in GMH as we discover more things that hotspot does under covers, right? We, as the performance guys, when we are presented with the external benchmarks, first thing we do, we rewrite the benchmark under GMH because that validates it. And most of the external benchmarks are broken badly. And we just, by rewriting it with GMH, we do have half of the due diligence that we have to do, right? And it also makes the benchmarks very reusable, so it facilitates the peer review, right? So the sneak peek for the GMH API is like this. If you want to measure something, you just make a method. You just annotate it with the annotation, right? And let GMH do the other stuff. So the GMH will generate a lot of synthetic code around that body, which will do all the scaffolding that you need to do the proper benchmarking. What's actually there, we will talk for the rest of this talk. Annotation processors, by the way, are quite limiting for the tasks that I need to do sometimes, but it's workaroundable. Okay? So the major trouble with the benchmarking is that it amplifies the effects visible on the same scale. So in that way, micro benchmarks are not really that evil because there are not so many effects that are visible on microsecond level. The nano benchmarks are the beasts when you are starting to deal with all this madness around memory, CPUs, pipelines, and all that stuff around, right? Pika benchmarks, just don't even get me started on this. I didn't see any viable Pika benchmark yet. OK, so I want to ask you a question. What is Warmup? Do you know what Warmup is? Yeah. It's just what makes Lambda forms perform so bad. Yeah. Right. So most of the people not in this audience, thank God, will tell me that the warm-up is waiting for the methods to stop compiling, which is obviously wrong. So the definition is warm-up. We have the dynamic processes. We have the transient processes in our runtime. So the warm-up is just waiting for these responses to settle down. So we reach the steady state, right? And every online optimizations that you have, not only counting the JIT compilation, does require warm-up. So if you see, many people like to refer to the Brian's article somewhere and say, OK, you just watch print compilation, and when it's over, you're done. This is not true. Yeah, I know that isn't what Brian actually intended to say, but that's what people read, right? So this is wrong, right? Because for instance, you have, this is the benchmark scores for Nashorn. And the x-axis is iterations, and the y-axis is the execution time. So you can see there, so you have the multiple warm-up plateaus, as I say, right? And so your end result will depend at which iteration you will cut the measurement, right? So if you're lucky or dumb enough to cut the measurement right here, you will miss this plateau, right? And it bears the question of what is the performance of Nashorn given these 5 plateaus, right? So warm-up is somewhat tricky. You can't, there's no external metrics that could tell you that the system had reached the steady state. You just have to run it long enough and see that there is no other plateaus ahead of you, right? All right. Then we go for the major pitfalls that we have. I have this series of quizzes. I don't like to talk much, so I want you to think, right? So let's suppose we have the very empty benchmark with the GMH, and we are running on some system which reports 4 CPUs. And we have these scores there. And I have 2 questions. First one is actually simple. Why there is no change when I'm going for 4 threads? Right, hyperthreads. I actually have 2 real cores, and 4 CPUs there are hyperthreads. So my benchmark saturates the system very nicely, right? But I have a trickier question. Why the scaling there is not perfect? No, you could actually see from the counters that the cores there are not communicating with each other. Each one runs the distinct version of the benchmark. That's all fine. It should be 2.0. Why it's not? No, there's no synchronization. OK, here's the answer. I downclock it to 2 gigahertz, and I have the perfect scaling. Why? Because my operation system and my processors decide that if I run the single-threaded workload, I can actually run my CPU faster, right? So if I downclock it, I disable that feature in my processor, which is Turbo Boost, and I have the very flat time in which I have the perfect scaling, right? It got you by surprise when you run the scaling benchmarks otherwise. So why is that? Because that's the optimization which hardware vendors and operation systems are doing for us, right? They try to do faster job when they can. If they can fold in the thermal budget, they will run faster, right? But the downside for that optimization is that we don't have the flat time anymore. In every single moment that we benchmark, we could have another CPU frequency or whatnot. So what we do, we disable power management, or we fix the CPU frequency. From the GMH side, we as the GMH maintainers are trying not to block threads most of the time. We just wait in the busy loops, telling operation systems that we will need this thread all of a sudden right now, okay? The trickier one is operation system schedulers are also balancing powers. Solaris is very good at that. He actually says, when I start the young thread, I will not schedule it on the distinct core because I don't want to wake up that core and waste some power there. So I'll just wait, and if it's alive for like a second, I will schedule it there. So if you run very short benchmarks when you start all these 50 threads, you will actually run all the threads on this single package or a single core, which will significantly offset your benchmarks, right? So the remedy is know your scheduler, and for the GMH, again, we don't park threads, and letting scheduler know that these threads are actually active, and please schedule them appropriately, right? Time sharing. We have time sharing systems. We try to balance the utilization of our hardware, right? By that, we are defying the control of our workloads to the system schedulers. When we say we are not monopolizing the particular core, but instead we go to the scheduler and say, OK, here's our workload. Please run it. Or please don't start the screensaver all of a sudden. But the downside for that is that the thread starts and stop are not instantaneous anymore, right? We just need to wait for scheduler to react. And it gets really interesting when you're running multi-threaded benchmarks, because you can start the measurement in all these 50 threads. And the single thread could start early and have all the caches, all the thermal budget that it can has, right? All the network capacity, all he wants before all these other threads start up. And that significantly offsets the mean of the benchmarks and also provides you a lot of noise. And the GMH has the remedy for that. We call it bogus iterations. When these are the distinct threads. When we are doing the bogus iteration before actually starting the measurement, and let GMH only measure the performance where you 100% sure that all other threads are running, right? So all these green measurement things would be only running when all other threads are up. On the large machines, you can have like 30, 40% difference between these two modes, which is kind of bad if you want to measure the effects of 10%, right? And that's for free. OK, I have another quiz. Suppose you have these 3 methods. One of these is obviously wrong because it's called measured wrong, right? And you can say this is wrong because the scores for these 2 methods are the same. And here I have the 32 nanoseconds, which is roughly how much the math log actually costs on my underlying platform. So what's the optimization I'm looking at? Dead code elimination, yeah.
Because we're in the JDK, in JavaScript, we still have to have a guard to see that somehow it has changed.
Thank God. All praise the JavaScript. Right. So the compilers are really good at eliminating the redundant code, right? And that's the problem if that redundant code is actually what you benchmark. So the remedy for that is either you consume the results or provide the side effects on the results in some way. In GMH, we have the API support for that, right? Here, you can just return the value and let GMH handle it for you magically. How it does it, we will talk a little bit later, like now, right? So the dead code elimination is rather easy for primitives when you do your own micro benchmarks, because for primitives, you have the binary combinators. And those are cheap enough, right? But if you do nano benchmarks, the combinator cost starts to get into the way, right? Even summing up 2 integers could come into the way, right? And also, the very weird result, if you have the low-range primitive like Boolean, you enable compiler to speculate about its value. It's not easy to speculate about the value of integer, but it's rather easy to speculate about the value of Boolean, because it doesn't really blow up your generated code. Right? So this is what people usually do if they want to consume. They accumulate the return value somewhere and provide some effect on the accumulated value, right? For objects, it is not that easy, because you don't have the fast object combinator, right? And also, if you want to do benchmarking properly, you have to escape the object. So all these fancy object optimizations are not kicking in, right? So you need basically to escape that object somewhere. But if you do that naively, like storing it on heap, Then you have the trouble that you have the heap write, which most of the time entails the store barrier, which costs like 100 nanoseconds, which makes the nano benchmarks notoriously hard to get right. How to deal with this? So in JMH, we have this magic class, which is called Blackhole. Its only duty to consume the values. Consume the values in the way that the dependent computations are not really DCE'd. So we do this sort of magic there. And users can request the explicit black holes if they want. We are implicitly feeding that return values from the micro benchmark back to the black hole. So the black hole design is deceptively simple. So for the primitives, we do something like this. When we do, OK, we have this incoming value. We compare it with the two other guard values. This predicate is always false. We as humans know that, because those are 1 and 2. And no integer could be equal to both 1 and both 2, we break the speculation because G1 and G2 are volatile, so compiler could not actually guess whether those are 1 or 2. And we use this bitwise AND because we don't want to do additional branch there. And for compiler not to say that this if does nothing, so if there's the empty body, I could just say, OK, there's no side effects for this predicate, and I could just remove it. So we have to provide the side effects. I could not throw new runtime exceptions here because the code generation would look different. So I have to do this VM trick of saying, OK, this is the implicit null pointer exception. But that's not. OK. So this costs like a nanosecond per call. Yes?
You can try throw neural.
Throw?
Throw neural.
Oh, yes, I could try. Yeah, but the trouble with the generation is the generating all these exception tables and whatnot. So the problem is having throws, not really the exception. For objects, can I do the same for objects? No, I can't. Because if I do the object here, and I feed it new object, escape analysis is actually smart enough to figure out that the new object, which is not escaped anywhere, comparing it by reference with any other object is always false. And it will just fold it if and fold the entire thing and get rid of the object, and everything breaks badly. So we have to store objects, but we can't store it frequently enough. So we have to do this kind of trick when you have the inline pseudo-random generator. It's remarkable how many technical problems can you solve with a good random number generator. So we do the stores every once in a while. We also try to, this is kind of the exponential backoff for these stores. And the reason why it's required is that we don't want hotspot to think this branch is actually cold and generate the trap there and do all sorts of object optimization before, So we have to have this branch hot. Yes?
Wouldn't it be, can you go back one slide?
Yes.
Wouldn't it be simpler to do the thing for object and just compare G1 to G2, which will always be false, and then store the object in the field? Would be public.
I'm sorry, you want to do what?
Compare G1 to G2.
Yes.
And if they're equal, which they can't be, store the object in the field.
Yeah, if you do that, hotspot would actually smart enough to get this predicate before your instantiation, and you're dead basically. So there's the tricky stuff that's going on. Every single change I do there, I have to validate it on many things. Yeah, but that's the price I pay for building this harness, So for objects, it's like this. It costs like 3 or 5 nanoseconds per call, so it's pretty decent to do micro benchmarks, Another quiz. So we have roughly the same benchmark, but measure wrong is wrong because it's just 2 times slower than baseline, while the real cost, as we established in the previous experiment, is actually 34 nanoseconds. What's wrong? What's the optimization? Yeah, it's constant, So compilers are good at constant folding, constant subexpression elimination, which I roughly call partial evaluation. And I know this is not the actual partial evaluation, So what we do to avoid this, we need to make the sources unpredictable in some way. And JMH, we have the special support for that. The generated code, which actually calls that method annotated with generate macro benchmarks, is running in this loop. And this is the volatile Boolean. So we break the commoning across the different calls. So if I read everything from heap every time in this method, I'm actually fine. Right? That's just a cool trick there. Up until Hotspot would be smart enough to actually unroll this while loop and do this all sorts of speculations about volatiles, which it is not at the moment, so we are fine, right? But we are engineers, right? We are talking about whether the probability of failure is low enough, not about whether it not fails every time, right? OK, so when you think about this constant optimizations and the dead code eliminations, you can actually tell that those are in brothers-in-law, right? If you have this computation tree and it depends on the sources on the things, if you somehow forgot to break the constant optimizations on sources, then you lose the part of this computation tree that you want to measure. Yeah. And if you do that for sinks, so you enable the compiler to eliminate part of this computation right there, you also lose the part of the benchmark. So when you do a lot of benchmark, you start to see things, right? When you look at the benchmark, yeah, when you look at the code and you see that whether all the sources are actually unpredictable or all the things are actually not that code eliminated. So you're like stretching the benchmark on your preparation table so it will execute in full on every single call. Right? Next optimization. The guys who are familiar with Caliper would recognize this idiom, right? Let's say I want to measure how much time I spent with summing up two integers, right? Here's my expression that I want to measure. So I will run it Caliper style, right? And say this is the method which takes number of repetitions there. And so the question for you is whether the performance dependent on n or not.
May or may not.
Is it dependent on n? Why? Right. We can run it on the particular platform, like my laptop. And you will see that depending on n, you actually have very interesting results. So if the nanoseconds per call is just the nanoseconds for the entire loop. And if I divide it by n, I have the nanoseconds per add. When I look at that, I say, OK, this can't be right. 25 adds per nanosecond on my hardware. It just couldn't do it, right? It's just wrong. So what's that optimization is? Actually, that's loop unrolling. Yeah, that's strength reduction because I have a lot of additions after I unroll the loop. But the major thing is loop unrolling, right? And it greatly expands the scope of the optimizations. And if you know that particular optimization, particular iterations takes m nanoseconds, after unrolling, you can only say that effective cost is alpha m. And for alpha, you only know it's somewhere between 0 and infinity. And that's all you know, right? So if you have unrollable loops in your benchmarks, then you are in trouble. Yep. So the remedy is avoid unrollable loops. For GMH, it turns out that our mechanics of avoiding dead code elimination and constant folding is actually nulling out the effect of loop unrolling. You can unroll the loop, but there is no effect because you can't measure the computations between the iterations. Right? All right. This is kind of long. So we have the interface counter, which does increments. We have the abstract class, which provides us the baseline implementation, which just increases the counter. And we have two concrete implementations, M1 and M2, right? And we want to measure it right there. This is the sin that I was warning about previous slide, but it's important here, right? So we have two instances of these counters. And we have two methods, and this is how we measure it, right? So Do you think the performance of M1 and M2 is the same? No. Why?
It goes bimorphic.
OK, so if you measure it, you will actually turn out to be that way, right? And if you run it in a single JVM, the first one is significantly faster. I actually seen people that said that, well, we need to call our classes like M1, and you will have the performance boost, which is bad.
For speed.
For speed, yeah. Just use shorter class names, and you'll be all fine, right? So if you run the M1 again in the same JVM, you will get the same score. Why? Yes, because M1 was monomorphic. If I run those two guys in the forked VMs, I actually have back my 5 nanoseconds per op, right? So the dynamic the optimization is that dynamic optimization can use runtime information. The downside for this optimization is that we can have significantly different performance profiles depending on the conditions that we are running in, right? And so the remedy for that is it depends on what you're actually up to measure, whether you want to measure the worst case performance. And so then you have to warm up all the code at once and then start to measure each of the benchmarks. Or you want to fork the JVMs and run the workloads in each JVM. JMH provides both variants, so it's rather easy to do that. I'm kind of lazy to do this kind of thing when I do the benchmark by hand. So yeah, JMH does it for me. Thank God. All right. All right. This is another beautiful Nashorn performance data. Can you see what is? Can you say to me what is wrong with this chart? Well, I would say that these are at least two modes, right? I can show you another benchmark which is more telling, like Mondriel, right? When you have like more modes than two, why is that? Well, yeah, actually, that's the run-to-run variance. Why? It's a very tricky question. I would not answer why, actually. But I can tell you that this is the fallback from the optimization, which tells me that many scalable implementations in VM are inherently non-deterministic. It's way cheaper to provide non-precise profile information than accurately collect the accurate performance data from all the threads. It's significantly cheaper to not care about the order of the compilation than actually enforcing the order and get the ticket to each method, so to enforce the order. The remedy for that is you can do the all sorts of replay mechanisms in your VM or your runtime, but it's not really practical at many points. So you just have to bite the bullet and measure the run-to-run variance. There's no other way around it. JMH provides you with this capability. You can do multiple forks. It will aggregate the data from these multiple forks, yeah, and whatnot. OK? Inlining. Inlining is the Uber optimization. It's really good. When you inline, it's all cool, right? The downside for that is you can't inline everything. So you have to consider the inlining budget and everything there, the inliner decisions and whatnot. So the remedy for that is making small methods so the inliner can do smarter decisions about what to inline, inspecting the actual inlining trees to figure out whether you had inlined what you wanted and you haven't inlined what you didn't want, right? So for JMH, we are generating the code so we can actually peel the code loops in the small methods in order to get better inlining decisions. And also we have this compile control annotation which feeds back into the hotspots compiler oracle stuff, which can actually force inline. If only it wasn't broken on many builds and public GTK, it would be perfect. So this is the sample method which JMH generates for the test long method, which is annotated with GMB. It's really small, so we know that the most of the time you would either trip the invocation counter for this method and compile it, and you will certainly trip the back branch counter on in this loop and compile this entire method and inline this hot one, right? So most of the time, this is where the inlining budget starts. Yes.
Yeah, but here you trigger OSR, and OSR and method compilation doesn't use exactly the same optimization.
Yes. Yeah. This is why Warmup is required, right? Right. Next optimization quiz. Suppose we have this tree map, and we want to see how much it takes to traverse it. And this is why the example when I use explicit black hole in order to not to get this, dead code elimination for this value that I just got. I should probably use entry set there, but just stick with me at this point, right? So suppose we want to test it in the two configurations. One, when we are assessing this map exclusively, like every single thread has its own map and tries to assess it. Or we have one shared map and wants to see whether the tree map entails some concurrency control from within, which costs us something, right? And if we run it on my laptop, for instance, you will see that the exclusive axis is actually slower than shared one. That doesn't make sense, right? If I do the shared scenario, my collection has to do all this sort of concurrency tricks within, and so it should cost something, but it's not the case. Why? And silence was the answer. OK. So the trick here is we are running 4 threads on my 4 hardware thread machine because we want to saturate it, right, decently enough to do this sort of benchmarking, which means that I have 4 maps in one case and only one in the other case. Come on. In the other case, which means that the footprint is significantly different in these cases. And I'm not fitting in my L2 cache here. And so I have lower scores, right? So the bottom line is that if you want to do this kind of stuff, you have to try different problem sizes to actually see how the performance changes when you measure the performance size. We were just unlucky enough to get some stride of that data, right? So, and that's the optimization, right? If we didn't have the caches and we all have this flat memory, it wouldn't be a problem. The memory access cost would be the same for all the threads, and it all would be fine. But we have caches for a reason, right? We have the performance there. The downside for that is we have the significantly different performance profiles, whether you fit the cache or not fit the cache. So you have to track memory footprint. You have to consider all these sorts of whether you fit in cache or not, try different problem sizes, and et cetera, et cetera. OK? Next quiz. This is, by the way, one of the GMH hints when we can say we have the micro benchmark which references the 2 states. And the states, one of them has the scope benchmark, which says it would actually be shared by all the worker threads. And other is scope thread, which means it would be thread local, right? And we do this thing. We have the shared integer array. We got our thread local index from the global atomic, right? And we want to increment the integer in particular position. So the question here is whether the performance of this benchmark different going from single to 2 threads. Is running 2 threads faster than running 1 thread for this benchmark? No. Yeah, if you run it, actually, on the very large machine, which has 32 hardware threads, you will see something like this. And in this case, you have like 240x performance drop, just because you had overlooked this nice optimization that we have on our memory subsystem, which says, because we have high locality data, it makes no sense to have the caches which address the single bytes. Instead, we will address the large cache lines. The downside for that is if we have the inter-thread accesses within this cache line, we have the false sharing, right? So we can do all sorts of tricks. JMH actually pads a lot of stuff internally in the control structures, and it also auto pads the state objects for you, so you would not forget about this. Okay? I think that's the last one. Let's say you have the integer array a, and we want to compute this weird function on a. right? We have the sum over the module of each element. And we have two versions of this code. One that uses the explicit branch, and the second one that uses math.abs. Which one is faster?
With the branch.
With the branch? Who's for math.abs? So it turns out that both answers are correct and both answers are wrong. But let's see in the assembly. Yeah. Yes. OK. So in the assembly is that branched version is actually generating the branch in the assembly, and the math.abs generates the conditional move, right? So it's more tricky question of which is faster, a branch or a conditional move? Yes.
It depends on the unpredictability of the input data.
Right. So if we do this sort of pattern in our array, and we do either regular repetition of this, taking branches, or we shuffle it specifically, or we just sort it, we have drastically different performance. And the thing is, the conditional move is always provides consistent performance, right? Whether there is no distinction of whether you predicted the branch or not. And the branch prediction, if you predicted the branch, is actually very fast, faster than conditional move. If you don't predict it, then you are in trouble, right? So the question is, if you do the larger pattern, it doesn't really change. So if you do this kind of sorting algorithm research, you actually know that you have to try different shuffles of the data to have the understanding of the profile of this algorithm. Turns out it's not only about sorting, right? You have to have different data feed through your benchmark because you can exhibit different branch prediction patterns, and that could offset your measurement, right? And that's the side effect of the optimization, because our hardware speculates a lot. When it succeeds, it actually runs very fast. When it's not, you have the very great artifacts for the mispredicts, right? So the remedy is only fitting it with the realistic data and all this data that you can possibly find and average over it. OK? So the conclusion is benchmarking is serious. Not that you don't know that, right? So you have to control the hardware. You have to control the operation system, the language runtime that you have running on JVM. You have to control the data, and you have to control the results. And you also have to control the people who are actually doing the benchmarks. Right? So JMH does one thing, and hopefully does it right. We have lots of plans to do for this microbenchmark harness. I think for this auditorium, I would try to say that we want bindings to other JVM languages, not only Java, in order to exploit this knowledge that we have included in the JMH. And so you will, proliferate and live and prosper. Right. That's everything from me. Thanks.